Assalamualaikum. Sorry. I actually I have recorded today's session until finish, but somehow, if you notice in the vibration isolation video, it finished uh, halfway, I think. So I have done until vibration absorber. So for this video, I'll just continue from where the first video stopped, and so you have to watch two videos today. Okay, so inshallah it will not be that long. Okay, so for this one, I think we finish with this one. Okay, and then oh yeah, so basically, as the conclusion for this one is that we want to select the best and most effective value of K and C, or damping, so that the vibration isolation will work at its best performance, so that it doesn't affect the so that it doesn't decrease too much, that it will make the spring basically doesn't work as a spring. And we also do not want to increase damping too much, that it will affect the performance of the machine. Okay, now and then we the other is basically for this one is if we have a if we want to isolate with the base input. Okay, this graph you can refer to the textbook to understand better. So, but I'll just skip this one. So this is isolation of source of vibration from surroundings. So if you want to isolate, especially if you want to isolate including noise of the vibration source from the surroundings, so we can use these equations. If you want to isolate system with flexible foundation, or okay, so yeah, so you can just read this one, but I'll just skip that one. And for example here, so if we have we will just touch on one example here. So if we have this exhaust fan rotating at 1000 rpm, which means so this one you need to convert to radian per second. Is supported by 4 springs and having a stiffness of K if only 10%. So you want only 0.1. So if it's 10% of the unbalanced force transmitted to the base, so you only want the transmissibility to be 0.1. Okay, only 0.1. So what should the value of K be? And assume the mass of exhaust fan is to be 40 kilogram. So so basically here we want the transmissibility to be 0. So based on the transmissibility equation, so we put 0.1 there. So we can basically we can also determine the forcing frequency, which is given to us 1000 rpm. So we can put it as 104.72 radian per second. So if we put all that in there, and as well as if we consider, in this time we do not consider the damping, so this zeta can be 0. So we only left with 1 over this equation over here. Okay, so also natural frequency we can also calculate from that. So we have the mass 40 kilogram. K, we should consider all 4 springs, so we have 4K here. And as again, assuming zeta is equal to 0, meaning no damping, only spring. So we can put everything in the equation, and to find imaginary values, so we in the end we get the spring stiffness to be just below 10,000 Newton per meter. Okay, so other than that, you can take a look at the examples, and the second type of isolation, which is active isolation or active vibration isolation, is basically we can be represented as this diagram over here. So here we have the motion sensor, basically to detect the motion of the base or the mass here, and the actuator. So the signal from the motion sensor will go through the whatever algorithm that we set over here, and from that algorithm and that controller, it will deliver the signal to the actuator to basically tell it um, have a certain displacement or a certain um, mechanism to isolate the vibration of the mass. Okay so so this one basically the main part for this second part is the vibration absorber. Okay, so vibration absorber is basically the extension of vibration isolation. So in vibration isolation, we simplify the system to be at one single degree of freedom. But for vibration absorber, is we since for the vibration absorber, we add another spring mass system to the system, to the existing system. So basically it becomes a 2 degree of freedom system. Okay, so why do we need a vibration absorbers? So for example, if we have a machine, or if we have a system that has an excitation frequency which coincides with the natural frequency, meaning for example, the natural frequency of the system is around 1000 rpm, and our excitation frequency is also 1000 rpm, or maybe close to 1000 rpm. So so if it stays the same when we basically excites the system, or the system is running, it will basically result in a very high amplitude of vibration. So you do not want that, right? So we want to have a mechanism to avoid that instance. So a dynamic vibration absorber basically is designed to shift the natural frequency of the resulting system away from the excitation frequency. So meaning basically, since we change, or since the system becomes from a single degree of freedom into second degree of freedom system, then it will have two natural frequency, right? So basically dynamic vibration absorber uh, creates another or creates a pair of natural frequency that is different from the existing natural frequency. So for example, if we have a natural frequency is at 1000 rpm and our excitation frequency is around 1000 rpm, so when we introduce the vibration absorber, basically it may become, the natural frequency may become 500 rpm and 2000 rpm. So meaning when at the excitation frequency, it is not in it is not it doesn't coincide with the natural frequency of 500 rpm and 2000 rpm, so it's in the middle. So basically we change the, or you can also say we move the original natural frequency of the system into two separate natural frequency, which doesn't coincide with the excitation frequency. Okay, so here is an example of a dynamic undamped dynamic vibration absorber. There is also damped dynamic vibration absorber, but we will not talk about that in this course, because that one is a bit more complicated. Okay, so if you remember existing system with only isolators, so this over down here, it doesn't exist, right? So we only have isolators. But if we want to introduce absorber, so basically we are introducing a new spring mass system into the existing system, so it becomes 2 degree of freedom, right? So from this system over here, we can derive the equation of motion first and second, right? So so we can assign we can assume the input to be a harmonic input. Okay, so the particular solution xj x capital X sine omega t, j is 1 and 2, and we can also derive our amplitude of masses. So this is basically the same as the second degree of freedom system that we went through before. Okay, and we want to reduce x1, right? X1 is basically the amplitude of the machine itself. So then we want to set the numerator of x1 to 0. We take the forcing frequency omega squared is equals to k2 over m2, and x1 and x2 can be rewritten as these two equations. Again, this is similar with the second degree of freedom that we went through before. And so basically, by using this line absorber, this line over here is basically the original natural frequency. Okay, so without absorber, so it has one natural frequency. So for example, here natural frequency is around 1 ratio of omega over omega 1 is 1.0, right? So if we introduce vibration absorber, basically it creates two natural frequencies which is outside the range of the original natural frequency. So meaning if our operating condition is somewhere here in the middle, then it is okay, because it doesn't coincide, because in the original condition the operating frequency is somewhere in the middle here. So basically, if the machine is operating, it is operating within or close to the range of resonance, meaning the amplitude will be too large. So if we introduce absorbers, basically it introduces two separate natural frequency, which basically if we look at this example, if our operating condition is at 1.0, then the amplitude is basically 0, right? So this range is safe for the operating condition. So basically it introduced two natural frequency, which is capital omega 1 and capital omega 2. So continue with the condition that we set. So x1 equals to 0, omega is equal to omega 1. So x2 we can derive as this equation over here, and we can find the size of absorber basically using this equation. Okay, introduces two resonant frequency, capital omega 1 and capital omega 2, and we can also use the notation of k2 over k1 is equals to k2 over m2, m2 over m1, m1 over k1, or this equation over here, m2 over m1 times omega 2 over omega 1 squared. Okay, so this one you might have to memorize. Okay, so if we set the denominator for x1 over delta st, static deflection, to be 0, then we can find the roots for the frequency. So in the end, we will get the two roots of it, the new natural frequency, omega 1 and omega 2. Okay, so this one actually I as well as, I think, which one stated here, no, okay, actually in the original slide this down here is omega 2, but I changed it to omega 1. Okay, so yeah, so this one you can take a look at this example 9.16, but I want to focus on this example at 9.17 because this quite interesting, because one thing this example shows the initial condition of the machine, what is the condition of it, what is the specification of it, and what is the countermeasure that was done. But then it is not enough, so you need to modify it from what has been done to a better one, right? So it's a two-step process. Now a motor generator set, this is a motor generator set. We have a motor and generator. is designed to operate in the speed range of 2000 to 4000 rpm. So the operating condition is 2000 to 4000 rpm. However, the set is found to vibrate violently at a speed of 3000 rpm due to slight unbalance in the rotor. So basically the resonance is around 3000 rpm. Okay. So basically it's in the middle of the operating condition, so this is what we do not want, right? So it is proposed to attach a cantilever mounted lump mass absorber system, this one down here. Okay, so we have a mass over here attached to a cantilever attached to the motor. And originally in trial, the cantilever carrying a mass of 2 kg, and it is tuned to 3000 rpm, so meaning you want it to work at 3000 rpm. And the resulting natural frequency of the system are found to be 2000 rpm, 2500 rpm and 3500 rpm. So basically introduces the two new natural frequencies, which is 2500 rpm and 3500 rpm. But then but this is quite it's still in the middle, right? It is still in the middle, which is not preferable, because it is still doesn't change the fact that the operating condition is still within the resonance area. So you will still experience resonance anyway. So from the original countermeasure, 2 kg of cantilever tuned to 3000 rpm, you want to design absorber to be attached so that the natural frequency of the total system fall outside the operating speed range of the motor generator set. So basically you want it to fall beyond 2000 to 4000 rpm. So it is better to change the condition of the top limit, which is 4000 rpm, meaning you want the natural frequency to be beyond 4000 rpm. Why don't we go for 2000 rpm? Because basically lower, if I'm not mistaken, okay, you can check this one, lower condition or lower limit is basically it tells the lower limit of performance of the motor generator set. So it needs to be somewhere from 2000 to somewhere up to the upper limit. So basically upper limit we can change that, but the lower limit sometimes it's not preferable to change the natural frequency for the lower limit, because sometimes that 2000 rpm. So if for example, if we set the if we set the natural frequency goes below 2000 rpm, sometimes the machine at its maximum capacity, or at its maximum performance is at 2000 rpm and above. So if we set it much below, then the system will experience resonance even before it reaches its sort of like a suitable operating condition. So you do not want that. You do not want that. So it's easier, or it's better to meddle with the top limit. Okay. So as I mentioned, I've done this lecture before. I have recorded before, sort of, but then I don't know, the system, the software doesn't capture what I am talking about. So I'll just repeat with the notes that I have written here. Okay, so from this example over here, so basically we have two operating natural frequency, or two operating frequency, which is omega 1 and omega 2. Okay, so omega 1 basically from the motor generator, omega 2 is the absorber, and M1 basically tells us the mass of the motor generator, M2 is the mass of the absorber. and we can take mu is equal to ratio between m2 over m1. Why? Because the original equation that we have over here, we have m2 over m1. So just to make it easier to write down, so mu m2 over m1 is equal to mu, so the equation will become shorter. Okay, so and we have the resulting natural frequency from the 2 kilogram absorber, which is 2500 rpm, and you have to convert to radian per second, which is 261.8 radian per second, and 366.52 radian per second, which equals to 3500 rpm. Okay, now the operating frequency is equals at before the absorber is attached is at 3000 rpm, and when the absorber is attached, it is also tuned to 3000 rpm. So our omega 1 and omega 2 is is the same, and which is in radian per second 314.16 radian per second. Okay, so we can put that into the equation of R1 and R2, which is omega 1, capital omega 1 over omega 1 and capital omega 2 over omega 2. In the example, it states omega 2. So either way, omega 1 is equals to omega 2, so it still becomes omega 1 as well, so it doesn't matter. So here we take capital omega 1 and omega 1, so we have the ratio 0.8333. R2 is 1.1667. So we can take either one and we can use this equation. Now before we can design a new absorber, we need to know all the specification and parameters that is available for us to decide. So in this case, what we do not have is we do not have the mass of the generator set. So we can find that from mu here. Okay, so since so we can take either R1 or R2, so it doesn't matter. So for example, if we take R1 and mu is m2 over m1, so here from the same equation, this one, we can simplify with this equation over here, and we put into the value of R1, so basically we get 0.1345. so this is the ratio between m1 over m2, and since we know m2 is 2 kilogram, right, so we can find the mass of motor generator set. And again, we take this equation as equation 1 because we are going to use it later on. So so right now, so like I said, this is a two-step process. So the first step is the current condition. So we have determined what is the current condition. So mass m1 is 14.8699. we know the absorber is 2 kilogram, and so on. Now then, next step is we want to design a new absorber. So the new absorber, we do not know what is the range that we should use, but we do know that we do not want to meddle with the lower limit. So the lower limit is 2000 rpm. So from there we can find the lower limit of our natural frequency, which is capital omega 1, 2000 rpm, which is 209.44 radian per second. So using this value over here, we can find what is R1. We know omega 1 is still the same, 3000 rpm. So R1 is 0.6667. So if we substitute this value into equation 1 over here, we can find mu. Okay, so we can find mu, and we can use the mass that we calculated for the motor generator set. Then we can find, so this value over here is actually the value of mu that is calculated from here. Okay, so that will be 0.6942. So using the value of mu, the new value of mu, and the mass of m1 that we calculated before, so we know the new absorber should have 10.3227 kilogram of mass. Okay, so this is the new absorber mass. So just to make sure if this mass actually will result in having a natural frequency beyond the operating condition, which is more than 4000 rpm, is we use the value of mu that we calculated before, and we find R2. Okay, so you put the mu in there and we find R2, which is 2.2497. so using this equation, we put into this equation for R2, so meaning we have R2 is equals to omega 2 over omega 2, right? So omega 2 is still the same, is 3000 rpm. So using that values, in the end we will get capital omega 2 is actually 4499.4 rpm, which is 500 around 500 rpm more than the operating condition, which is 4000 rpm, right? So in this case we can use this mass. Next is to find what is the suitable stiffness according to this mass. So we can use this equation here. So K2 is the new or the new absorber's mass, new absorber stiffness. Omega 2 is again the operating condition, and M2 is the new absorber mass. So we can put that into the equation and we'll find K2 is equals to 1 times 10 to the power of 6 Newton per meter. Okay, so this is our new set of specification for the new absorber, if we want to have the natural frequency to fall beyond the operating condition. Okay, so what this means is that the natural frequency falls or basically you will have a much broader range of operating condition that you can use for this motor generator set without coinciding with the natural frequency. Okay, so this is dynamic vibration absorber. So this is just as a reference, you can take a look if you want. This is a bit more complicated than the undamped dynamic vibration absorber. Okay, and last but not least is your assignment for today. Okay, so please try out this assignment and please submit within the due date. Okay, so thank you very much. Sorry for any shortcomings. We will have at least another one, not at least at least another one session, and if we have time we'll go I will do some tutorials. Okay, so thank you very much. We end with tasbih kafarah wa ta'ala subhanakallah wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. wal 'asri innal insana lafi khusr illa alladhina amanu wa 'amilus solihati wa tawassaw bil haqqi wa tawassaw bis sabr. Assalamu alaikum warahmatullahi wabarakatuh.